fun stuff too. That's basically it. But there are wonderful processes within those star-forming galaxies, like supernova at the end of stars' lifetimes, that blow stuff out very, very energetically. Sometimes that gas rains back down onto the galaxy's disk, its star-forming stellar disk, to form future generations of stars. So we as astrophysicists need to understand this process if we are to ever have any hope for humanity to understand the ways that galaxies evolve over time. The stuff that forms stars, the stuff that forms planets, the stuff that life comes from. This galactic gas cycling process is extremely important for us to understand that. And we have no idea what it actually looks like.
Oh, sorry, my fault.
Oh.
Okay, try again.
Hey, there we go. All right, scary slide, but bear with me on the graph here. So this is showing us what we as astrophysicists know from simulation. So we have really fancy computers and we can simulate what the gas in a galaxy looks like, that whole circumgalactic medium. So if we were to take just the CGM of a galaxy and look at its temperatures, remember simulated temperatures along the y-axis of this figure, and simulated densities of this gas along the x-axis here, we have what's called a phase diagram. So sometimes astronomers say the CGM or circumgalactic medium is multi-phase, it means all these phases.
Oh
no! Thought I almost had a shot to catch it, but no.
It's not a space draft show without some kind of drama. It's every time. Every time.
You're right. I don't think I've seen a cloud for the last 3 weeks and suddenly we have rain. So.
This is what we do. We generate rain for Tucson. Every third Tuesday, rain for Tucson.
This is the rain dance, yeah?
Yeah.
All right, onward. All right, phase diagram. So the grayscale on this is showing the mass of a simulated circumgalactic medium. And if you look on the y-axis here at all of this gray stuff in the background there, all of this gas, or a huge portion of this gas, is at a few times 10 to the 5 Kelvin, so 100,000 degree gas. That's going to be our magic number for this talk here today. So much of the mass in galaxies in the circumgalactic medium is holed up in this a few 100,000 degree phase. We call this phase the warm-hot phase because, remember, astronomers are the least creative people on the planet. It's between the warm phase and the hot phase. Warm phase gas is about a few times 10 to the 4 Kelvin down here. Hot phase gas is 10 to the 6 and up. Okay. Now, if you're looking at these wonderful, confusing, colorful squares here, long story short, these are atomic line transitions that are fingerprints to help us study different regions along this phase diagram. So if we want to study this few times 10 to the 5 Kelvin gas, this warm, hot phase where all of this mass is, we got to look at one of these orange squares. I'm going to give you just the answer here in which one of these we're going to look for. We're looking for this O6 one right there, oxygen 6 from 5 times ionized oxygen. Long story short, it's the easiest one to observe, but it's by no means easy to observe. Okay, so that's from simulations. From theory, we think we know what the CGM should look like and where all this mass should be. Now, what do we actually see when we point our telescopes at stuff? What do we see in observations empirically? So the vast majority, and by vast majority I mean almost all of what we know observationally of the circumgalactic medium has come from what's called quasar absorption lines, or absorption line studies in general. Oh, the sail is coming. I can see it almost tilting again.
We got sandbags now, so.
Yeah. I'll just stand in front of it. So what are these absorption line studies that we know what we know from? So you take your favorite optical telescope. Most of the time, historically, this has been the Hubble Space Telescope for the vast majority of these studies. You point it at your favorite background quasar, which just so happens to be behind the CGM of a foreground galaxy that you're interested in studying. So off the bat, let me explain this a little further. So the light from the quasar, picture a light bulb behind a cloud. The light from that quasar, as it travels from that quasar towards this galaxy, is absorbed by the atoms, is absorbed by the atomic constituents, the structure of this intervening foreground galaxy. So we can use the fingerprints of absorption. Yeah, we can use the fingerprints of absorption. From this gas to study the very faint circumgalactic medium and the atomic transitions that are happening there. Now, so what have we learned from studies like these? So we have learned that the CGMs, particularly this warm-hot phase of CGM gas, contains more mass than every star in the host galaxy. Tons and tons of mass. Extremely dynamically important. Again, this is why when you hear astronomers say stuff like, most of the universe is missing, we don't know where most of the universe is. It's because we have all this mass outside of galaxies, no clue what it looks like, we really don't know empirically what phase it's all in, we have some ideas, but no clue what it actually looks like. So if you're following along from studies like this, one caveat is you have to be lucky enough for there to be a background light source towards the line of sight to this object you're interested in studying. Because remember, we don't care about the quasar, we care about the galaxy in the foreground. But, as you can imagine, we don't get lucky enough very often to have these quasars behind the things we want to study. So, right off the bat, that's a limiting issue. Secondly, you only have information along that one line of sight to that quasar. So if you want to study anything in 2D space, images, morphology, you're SOL. Can't do it. So in essence, we do not have eyes on the dominant matter component of the universe. So I'm not the first person to have come up with this.
Oh my gosh!
We got
Holy
a real monsoon
cow.
here, guys.
This is a real storm.
Anyway, so I'm not the first person to come up with this idea. This has been a well-known issue in astrophysics for a very long time. In fact, all the way back in 1976, Lyman Spitzer said, while the hot gas observed with Copernicus is very similar to the extended corona, suggested nearly 20 years ago, the origin and spatial distribution of the observed coronal gas is not at all certain. So since the 70s, it's been over 50 years we've been thinking about this stuff. So why haven't we been able to solve this problem yet as a field? Well, the answer is likely three things. One, that oxygen 6 transition that I mentioned before, that perfect fingerprint for us to study this stuff, that fingerprint emits light in the far ultraviolet. So remember, light like the stuff you see with your eyes is not the only types of light that's happening all around us, that's being emitted, absorbed, all that fun stuff. There's infrared. If you put infrared goggles, you can see heat. The UV is on the other end of the spectrum, a lot higher energy and a lot bluer than blue, hence ultraviolet. So immediately, shout out to the ozone layer. It's awesome. It keeps us from getting cancer immediately. But it also keeps us from ever seeing these photons from Earth. So if we ever want to observe this oxygen 6 gas, these photons, the fingerprint of warm hot gas emission, we got to go to space immediately. Got to get above the atmosphere. That light's also hella faint. So it's extremely difficult to observe as it is. You need hypersensitive optical systems to be able to see this stuff, and you're sitting and staring at single fields for literally weeks at a time to detect just a couple of photons. And this last one is a little bit more subtle. There's an element of luck to this that I believe may have been biasing some of the past results from the absorption line studies like I mentioned before. So on the left-hand side here, this beautiful picture you have been seeing is an actual simulated galaxy just in that warm, hot oxygen 6 component of the CGM. So the stellar disk lies along this horizontal axis there. And these filaments are actually oxygen-6 circumgalactic medium filaments. So if this galaxy is a representation of the real world, what real external galaxies look like, if you were to just point your telescope at a quasar over here, or in region beta, you wouldn't see anything. But if you point your telescope and have a quasar at region alpha, you get lucky and you detect something. So the quasar absorption line results could be biased to making us think this is harder than it is, just to say. Now, adding fuel to the fire here, ultraviolet optics and detectors are historically just terrible in terms of efficiency, and it's really, really hard to get something into space. Until now. So, in the last 10, 15 years or so, there has been an extreme push and a huge revolution in ultraviolet technology and access to space. Just how in the last 10 minutes we've had more rain than the last month. So can you guys hear me in the back okay? Yeah, alright. Screw it, we'll just keep going.
Soldier on.
Alright, so what's been going on in the last 15 years in UV astrophysics? So, there has been leaps and bounds in detector technology. So on the lower left here, electron multiplying charge coupled devices, EMCCDs, are being developed right now at NASA JPL in LA, in Pasadena, California, by Sholay Nitzat. And Erica Hamden, right here at University of Arizona, develops these EMCCD detectors as well. Manuel Quijada, his group at NASA Goddard Space Flight Center in Maryland. This is Manuel inside of his coating chamber where he coats ultraviolet optics for high reflectance. So if we want to make a telescope to observe ultraviolet photons that are very, very faint, we need optics that are very good at reflecting those photons. And that's what Manuel does. Microchannel plate detectors have been getting smaller and smaller. MCPs are really, really old, archaic technology in a sense. They've landed on Mars, they're in orbit around Jupiter as we speak. But the key point being, they're getting smaller and smaller for us to put on small spaceflight platforms. And of course, in the news, SpaceX, the Falcon 9, and NASA's partnership with SpaceX in the SmallSat rideshare program has dramatically reduced the cost of sending small payloads into space. And so in this new paradigm that we're currently living through, that I've been calling the Wild West of space astrophysics, Aspera was born. So Aspera, my wonderful little mini fridge in the sky that will float and tell us all of the wonderful secrets of the CGM. So here's a quick view of the Aspera team. I'm not going to read all the names, but I'll just say I'm Carlos Vargas, I'm the PI. Erica Hamden is the deputy PI, another faculty member. She's sort of second in command. Han Chung is the project scientist. And Tom McMahon is the project manager. And as you can see, the team is solidly centered, managed here at the University of Arizona, just right down the street. And I'll also point out the coloring scheme. You might see some names are hard to read. The color coding here is blue for early career faculty and postdocs, orange for graduate students, yellow for undergraduates, purple for early career technical staff and engineers. And you'll be very happy to see as well, we are over 50% early career. We're one of the very few NASA projects that are actually mostly early career. This is something I'm very proud of. I also...
This is wild.
I also got to shout out ANT, Ascending Node Technologies, is one of our partners. This is another local Tucson company that is helping us with flight software, concept of operations, orbit selection, all of that fun stuff. So shout out to ANT. So hot off the press, you guys are among the first people on the planet who aren't on the team to see our final CAD design for our spectrograph, the payload. the instrument that will take these measurements for the very first time.
Holy shit.
And here's what it looks like. Now, it's going to be challenging to see where everything is, but... Oh, we've got a roof leak.
Oh no!
We'll survive, y'all. All right. Main components of the spectrograph. So we have, if you follow the path of light here... I'll give everyone a second to relink it.
My computer! Go ahead and finish.
All right, onward. Let's go. So main components of the spectrograph. If you follow the path of light through the two identical entrance apertures, you'll eventually hit an OAP, off-axis parabolic mirror, that is coated with enhanced lithium fluoride. Remember that higher reflectance UV coating? Bounces light to our gratings, which act sort of like a prism to separate the light into its colors. And then those colors
Here's power? How? Nothing else lost power. I don't know. Nothing else lost power. Is it because the plug is down there?
I bet you our entire electronics just got shorted.
Huh?
I'm looking at the biggest one.
Yeah, I think it's because our plug is down there.
Welcome back!
Hold my beer.
Doutor, e que maldição tu traíste pra cá que tu está você? Você não estava allá porque você trae cá, você lembra? Stream was running late, I was trying all the undergraduate people. Well, you didn't miss much. No, just that, I've been up in the last 20 minutes. Yeah. Oye, son las cosas. ¿Y dónde traiste el huracán contigo? No, dale.
Do we know where this is going? Do we know where this is going? Okay. Do they have another cord?
Show does 3 speakers and astronomy in the news every, or they used to. I'm gonna stop the live stream.
Try out and try it again, or
Alright, maybe we'll still do business. Okay, good. Woo! No, yeah, Susie trying to jury rig something. I know. She's a badass. I've been live tweeting our drama. Carlos talking, and then he was like sail. Yeah, just like lightning.
I for sure thought when it stopped before. I surprised we got our like.
That's what my weather app said. My weather app said peak rain chance 7 p.m. Goes down to 0 after that.
Well.
Tucson is full of ice. There was a cluster of people just standing there with you to talk. That is interesting.
At the end, they were there.
That is interesting to CGM, let me tell you.
Yeah, it's interesting.
We love them some CGM.
I do not
I am so nervous for Susie. She's a badass, but like, I'm still nervous for her. Is that tripped? you? Is it?
I connected it to Cam Link. It should be working.
It is not.
Cam Link is.
I'm just turning it off and on again. Cool. Nope, that's the. How did we solve this before?
It was info. Hang on. Tell me when it's on the menu.
Okay.
Is it on the menu?
Hold on. Now. There we go. Do it again. Again. Again.
Oh, good.
I love that we're just live streaming all this. I never stopped live streaming, so just live streaming it. I've been live tweeting all of this, by the way. I tweeted some good videos of Carlos talking while I pan over to the downpour.
Thank you so much for rolling with the punches. We should take you.
At least it's quieter now. What's up with the projector?
It's warming back up. It wasn't turning on, Matthew. I just switched the plug.
Uh-oh.
We got the power back up.
Yeah, I can see it's on. I just thought it would have shown something by now.
Yeah, how long does it take?
There it goes. There you go. You had to push that button. Huh? There it goes. Back in business.
What? Oh, just this?
Whole thing. Just all of this. My goodness. This is the wackiest space draft
This
ever.
is
Wackiest space draft
something.
ever.
See if I can get away with not moving screen.
The sandbags are gonna. Oh, one of them dumped everywhere.
Yeah.
Oops. Okay, are we ready?
I think so.
Yeah. Can you do some audio test? Oh, it got turned down. Okay, can you talk?
Test, 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 test. Can you guys hear me in the back? Way back? Oh, I see some thumbs.
Yeah, I see thumbs. I think we're good to go.
All right, hey everybody, we're back. So Mother Nature didn't cooperate for the first half, but looks a little bit better now. But maybe I should knock on wood or something. Anyway, let's pick up right where we left off, y'all. So as I was saying, you guys are among the first people who aren't on the team who are able to see this wonderful hot off the press CAD model of what Aspera actually will look like, since we're beginning the build of this instrument as we speak. So, following the path of light, because remember this is a telescope, following the path of light through these two identical entrance apertures. So light will come in from space through this way, come down these rectangular baffle regions. Inside of these rectangular boxes are specially engineered vanes that keep scattered light from bouncing around to get through the entire system of our telescope, because remember we're looking at extremely faint light, so any extra light that we don't want really screws things up for us. So as that light goes down right through the barrel, it'll hit our OAP, or off-axis parabolic mirrors, which are coated with those wonderful high-tech UV reflected, high reflectance coatings. They bounce to our gratings. These gratings sort of act like prisms, that separate light into their colors. But these gratings do that way more efficiently in a smaller package. And that separated spectrum of light, the colors of light, then gets sent down to our detector, our microchannel plate detector, which is at the heart of the instrument here. The detector is shared by both of these identical apertures. So what you see on this side is the same as on that side, except on this side we're showing like a cutoff where on the left-hand side, where that teal area would represent a shroud that covers the whole thing. So this is just so you can see the innards, basically.
Oh, sorry. My mistake. Okay. There you go.
Awesome. So we're not reinventing the wheel here. This is a design inspired by the FUSE telescope, the Far UV Spectroscopic Explorer, launched way back in the 90s when I was a baby. It's, again, 2x long slit spectrographs. This instrument, Aspera, even though one of these mirrors is only about 5 centimeters across, will be 2,000 times more sensitive than the Hubble Space Telescope's Cosmic Origin Spectrograph instrument for the purposes that we're using it. So that isn't to say we're way better than Hubble. Heck no, we're not. We're a lemon zester. Hubble is a whole kitchen full of tools. Do a lot more than we can do, but we're really damn good at zesting lemons. So this instrument is comprised completely of proven technologies. We're not testing new tech at all. We're using regular old optics for the most part, regular old detectors that have been flown a million times before, coatings that are pretty close to state of the art. And here, of course, banana for scale, so you can see roughly how big this is. This is a full 1-to-1 3D printed model of the instrument. And here's Afaq Khan, one of our wonderful graduate students, stealing the payload 3D model at one of our reviews. Okay, so what are we going to use this wonderful telescope to do? We're going to look at these galaxies to observe that oxygen-6 warm hot gas emission in the circumgalactic medium of the galaxies. These are 6 of our 21 total targets that we have on our target list, of which our mission is to observe a subset of 10 and map 3. And remember, 3 would still be 3 more than anyone's ever done, so this is a pretty big deal. You might notice a similarity between all of these. Anyone have any ideas on one similarity between all these? I see a hand in the back. What are you seeing?
Well, yeah, I was going to ask if they're all edge-on for any reason.
100% correct, yeah. So these are all edge-on galaxies,
Nice.
meaning we're seeing disk galaxies with their plane oriented, so we're seeing it from the edge on, sort of seeing the crust of the pizza, if you want to think of it that way. Now, why might we be looking at edge-on galaxies, which is your question? This is so that in projection, we can immediately distinguish what's in the star-forming disks of those galaxies, which you can see in these images, and what's in the circumgalactic medium, which would be above, below, outside of it. Because again, what we're interested in is seeing that CGM that no one's ever seen before. So who knows what lies in the dark regions of this image that we're yet to find? Okay, so what will Aspera be capable of doing? So here are some mock observations. So you can see our instrument's response, our system response. This includes things like spacecraft jitter, our resolution, that kind of fun stuff. So if we were to take this simulated galaxy that I showed way back before the Poseidon came from the sky or whatever, you could see these wonderful features in that simulated galaxy very clearly in our mock observations. Oops, sorry, I went too far. And the way that we build images like this since we are what's called a slit spectrograph. So our field of view is only one of these rows in this sort of diagrammatic showing you how this works. We build the image by going row by row for a super long time per row, and then building an image together like I just showed it stitched together there. So with Aspera, we should easily be able to distinguish these wonderful filaments that we don't even know if they exist or not yet. So what are some major technical challenges that we are running into right now as we build Aspera? So the biggest issue,